So, in the last class we discussed about the silicon control rectifier, which is one of the mostly used PNP device. It is also known as thyristor. So, the symbolic representation of the silicon control rectifier or thyristor is like this, as shown in this figure. It is having an anode, a cathode and a gate terminal. So, the anode is kept at a positive potential with respect to the cathode, and we trigger the SCR or the thyristor by means of the gate. We give a triggering voltage or to the gate and we fire the SCR, and due to this gate voltage being applied to the gate terminal, the firing of the SCR takes place at a voltage much lower than the breakover voltage that we have seen in the last class. So, again if we recall the VI characteristic of this SCR, we have this type of characteristic where we have seen that for the gate current Ig1 greater than 0, we see the firing taking place at a value of voltage lesser than the breakover voltage, and as you go on increasing the gate current at a smaller and smaller voltage, the firing will take place. Now, there are two specific currents which are the holding current and the latching current. These currents are carrying a significant meaning, because the holding current is the value of the current below which, if the current in the thyristor falls, then it will be turned off. That is, in order to turn off the thyristor, the current through the thyristor must be made to fall below the holding current. Similarly, there is a latching current. The latching current is important from the point of view that in order to keep the thyristor in the on condition, the current through it must be above the value of this latching current. So, at any time when we make the thyristor on and want to keep it conducting, then the current through it must not fall below the latching current. So, these two currents are important to keep in mind. Now, the turning off of a thyristor is one important point to be noted, because we cannot turn off the thyristor or the SCR simply by removing the gate signal. Even if we remove the gate signal, the thyristor will continue to conduct unless and until we specifically apply a method of turning the SCR off, and these methods are either by anode current interruption or by force commutation. That is, even if we remove the gate triggering signal, the thyristor will not turn off. We have to apply the method of making the anode current 0, or we will have to force the thyristor to turn off by making a current flow through it in the reverse direction by reverse biasing the anode cathode terminals. So, the anode current interruption is simply by making the anode current 0. It can be done by two ways. One is by series interruption, or the other is by shunt interruption. In series interruption, what is done is that we make the circuit of this thyristor open, and then anode current will be 0, thyristor will be off, or we can connect a shunt part through a switch, make that switch close, then the current will take the path through the switch which is closed, and then the current through the anode of the thyristor will be 0 and the thyristor will be turned off. So, these two are simple methods by which the anode current is made 0. It is interrupted either by series interruption or by shunt interruption. Another way of making the thyristor turn off is by force commutation. So, what is done here is that we have to make the current through the thyristor in the opposite direction. For example, in this circuit we have a transistor Q1 and there is a source, DC source VB, which is also connected in series with the thyristor. Now, when we apply a pulse as shown here to the transistor Q1, when the pulse is high, that is the application of a pulse to the base of the transistor will make the transistor turn on. There will be current flow in the collector, and what will happen is that now the current will be flowing through this circuit in the direction shown by this arrow, and what will happen is that this thyristor will be having now connected to positive terminal of the battery to the cathode, and the negative will be connected to anode. That means, we will be now having a current flowing through this circuit in such a way that the thyristor will be biased in a reversed way, anode cathode terminals will be not positive to negative, and due to this current flow when the transistor is on, the polarities of the thyristor are becoming positive to cathode and negative to anode, because as we see here the transistor is on. So, it is like a very short circuited part. So, conduction is taking place in the transistor, that is why current is flowing and making this thyristor off by making the polarities of the anode and cathode like this, just opposite or reverse biased. So, this is the forced commutation which also makes the thyristor turn off. Now, we are going to discuss some important applications of the thyristors. So, mostly we find application of thyristor in power control. When we are dealing with power, thyristors are mostly used for applications like rectification, phase control of AC, etc., because here one point to be noted is that we are having a high power. That means, we are dealing with circuits having connected to high power source. So, what benefit we are getting by using thyristor? That mostly we are getting the benefit of using thyristor in this circuits which handle high power is that the thyristors can handle high power, and even it is more beneficial to use thyristors for power control compared to even controlling by means of power transistors. It will be even cheaper to use thyristors in those cases of power control where we can use power transistors, but that will be mostly from the point of view of economics, that is, we will be having cheaper implementation using thyristors in the power control. So, let us see how thyristors can be applied for AC power control. For example, one typical application of thyristor is in AC phase control. The thyristor is used to connect AC supply to a load for a control fraction of each cycle. Suppose we are having a load where we are giving an AC supply, but we do not intend to supply the power to the load for the whole input cycle, only for a fraction of the input cycle. Suppose we want to feed the power to the load. In those cases, we will be applying thyristor for this phase control of the AC. That means, for example, we are having an AC voltage. Suppose this is a sinusoidal AC voltage we are giving to a load, but we do not want that the power supply to the load should be continuously for the whole input cycle. Suppose we are applying a Vs supply voltage, which is AC, which is given by say Vm sin omega t. We are taking typically an example of a sinusoidal source. Then if we do not want for the whole input cycle the load should get the AC power, we can control this supply of AC power by means of a thyristor. So, that is the application of thyristor for power control. Here, suppose we want to apply the power to the load for only one portion of the whole cycle. Then what is done? By principle, how it can be achieved? We will be using a thyristor, because we can precisely fire the thyristor at a particular angle of the whole input cycle by properly choosing the triggering voltage. So, the thyristor can be fired precisely at one point. So, suppose for example, we want the thyristor to fire at an angle of alpha. So, this angle of alpha is the angle at which we will be turning the thyristor on by using the triggering signal. So, what will happen is that at this angle alpha, the thyristor will start conducting from this angle alpha, which is known as angle of delay, and it will be conducting after this alpha angle. Then let us take this conduction period or conduction angle as beta. So, we have the thyristor conduction taking place from this point to this point, that is for the conduction angle beta. So, at the point of angle alpha, that means at this angle it is say 0. So, here at this point alpha means after angle of alpha, that is a phase angle, we are firing the thyristor is turned on. Then after this point it will be conducting till the value of or the angle of beta. Now, what will be the voltage of the thyristor? It is 0. Although the voltage after turning on is a very small voltage, not 0 to be precise, and normally it is greater than the diode on voltage. Normal diode has the voltage after conducting around 0.7 volt for silicon, but for a thyristor that voltage after conducting or after turning on, that conduction voltage is greater than normal ordinary diode, but for all practical purposes we will be considering this voltage to be 0 because we are dealing with power circuits, power control. So, the voltages which we will be handling are quite large. So, in comparison with those voltages, this small voltage of the thyristor after conduction can be very well assumed to be 0. So, as soon as the conduction takes place, the firing occurs in the thyristor, the voltage becomes 0. Before the thyristor getting fired, the voltage will be equal to the input voltage to the thyristor because there is no conduction, no current is flowing in the thyristor. So, the non-conducting thyristor will be having a voltage equal to the input voltage. So, during this portion you see the voltage is equal to the input voltage. After that point of firing, the thyristor voltage becomes 0. So, this is the principle which will be applied for power control. So, what we are discussing is the AC phase control. That means, we want to supply an AC power to a load not for the whole input cycle of the input voltage, but for a limited portion. So, typically one circuit demonstrating the phase control using thyristor is shown here, and we are taking a resistive load in the beginning for simplicity. So, we will be understanding how the phase control is being achieved using resistive load and then we will be also discussing about an inductive load. So, now in this circuit we are applying the AC sinusoidal voltage which is ES, and this thyristor is connected to the resistance R, and let us take the voltage across this thyristor being as ET, and R is the load, and the voltage across this load R is say EL. Now, let us apply sinusoidal voltage which is ES. It is a voltage which is say V sin omega t type of voltage which is sinusoidal. Now, the thyristor is fired at an angle of alpha. So, initially when the thyristor is not fired, it is not conducting, the voltage across the thyristor which is ET will be equal to the voltage ES. That is why this voltage from this point to this point is exactly same as this voltage. Now, at the angle of alpha which is the delay angle, the thyristor is fired. So, when the thyristor is fired, then current flows through the thyristor is on, and the voltage across the thyristor is 0, that we have assumed it is very small voltage and we can very well assume to be 0. The conducting voltage or the voltage after turning the thyristor on is 0, that is why it will be dropped down to 0. It will drop down to 0 and be 0 till the point when the input voltage becomes negative, because you know that the thyristor is turned off if the anode is made negative with respect to the cathode. So, if in this circuit if we see the moment the voltage ES is a sinusoidal voltage like this. So, this is positive half cycle, this is negative half cycle. So, in the positive half cycle, by means of this triggering voltage at the gate, we are not now discussing the methods of triggering, we are assuming that a triggering voltage is applied at the gate to fire the thyristor at an angle of alpha. The delay angle of alpha is maintained. What method of gate triggering is used, that is another topic of broad discussion. So, we are not going to discuss those methods of triggering, but simply assuming that is being triggered by suitable method for getting a delay angle of alpha. Now, when this is triggered, it is in the positive half cycle, it is triggered at an angle of alpha. So, this is angle of alpha where when it is triggered, and the moment it is fired or turned on, the voltage across this thyristor, that is ET, it will become 0. Now, the thyristor will be turned on and it will be continuing to be on till the point when the input voltage becomes negative. In this negative half cycle, when it is crossing the 0 and becoming negative, then the anode becomes negative and the cathode becomes positive. So, there cannot be the conduction or the firing of thyristor, it will be stopping conduction when anode becomes negative with respect to cathode. So, it will stop conduction, current becomes 0, and that is why the voltage across this thyristor, which is ET, it is nothing but this supply voltage. When it is not conducting these 2 points, if we consider the voltage across these 2 points is nothing but this supply voltage, and that is what is shown here. From this point onwards, the voltage across this transistor is equal to the supply voltage ES, and the conduction angle is beta. We have already assumed alpha and beta to be the delay angle and the conduction angle. And if we look into the voltage across the resistance, the load resistance R, the voltage across the load resistance, as you can see, what will be this voltage? That voltage equal to the current into the resistance. The current which is flowing in this resistance will be following the input voltage shape, because it is a resistive load. So, if we find out this EL, the voltage across this load, we can see here that till firing occurs, till the thyristor is turned on, the voltage across the load is 0, because there is no current flow in the resistor. So, the voltage will be 0 from this point till the point of firing, and as soon as the thyristor starts conduction, current flows in the resistor. So, the voltage across the resistor is nothing but the supply voltage, because the voltage across this thyristor is 0. When it starts conducting, the voltage becomes 0. So, the voltage across the resistance and voltage across this in the supply voltage are same. So, that is why the shape is exactly same and magnitude is same. That means, it is following the supply voltage only till when, till again when the till the point when the, actually this is this type of, this will be 0 only after this point. So, from this point again the thyristor stops conducting. So, the voltage across the load will be 0. Similarly, if we consider the current in the thyristor, this current IT which is flowing to the thyristor as well as the load, the current will be following the voltage signal because it is a resistive load. So, only the magnitude will be less, but the shape will be exactly same as the voltage across the resistance. So, EL by R, that will be the current, that current is flowing through the circuit as well as the thyristor. So, it will be, this is the voltage EL and it will be the current. So, till the firing of the thyristor takes place, it become current becomes 0, current is 0, no conduction is taking place till alpha, and after alpha that conduction starts, current starts flowing, the voltage across the resistance is of this shape. So, current also be with of this shape only because it is a purely resistive load. So, in this figure we have seen that the voltage and current across the load is present only for this portion in the whole half cycle, and even in the other half cycle it is totally 0. So, if we consider the input waveform of ES, we are getting the output waveform for only a small fraction or only a portion of the input wave. So, we are basically giving a control power, we are controlling the power input to the resistance, because voltage and current, these are control, means we are not allowing the whole input voltage to be supplied to the load, we are only applying a small portion, as well as the current is also present for a small portion. So, the power which is voltage into current, that will be also only present for a portion of the whole input cycle. And as we are using a resistive load, it is very obvious in the figure that beta equal to 180 degree minus alpha, that is the non-conducting angle which is alpha is 180 degree minus beta, or the conducting angle beta is equal to 180 degree minus alpha. Alpha plus beta is equal to pi. That is because of the fact that we are using a resistive load. But if we do not have a purely resistive load, suppose we are having a load having resistance and inductance in series, we are having an inductive load or a complex load, then this will not be the case, because in inductive load the current will not immediately stop to become 0 as soon as the thyristor stops firing. Because of the inductance, the current will still be flowing for some more time, and this effect will be causing that beta is not exactly 180 degree minus alpha. The non-conducting and the conducting angles, if we consider, as we are getting in this resistive load, that beta is equal to 180 degree minus alpha, that will be not true for complex loads. Now, the AC to AC converter is a device where the phase control technique is used to control the AC output power fed to an AC load. We are considering a load which is getting an AC power. Now, the AC to AC converter using thyristor does the controlling of the AC output power to an AC load. How it does so? To understand that, let us consider a circuit having two thyristors T1 and T2 back to back like this, as is shown in figure. We are of course considering single phase AC to AC converter. So, we are considering a single phase AC to AC converter, means we are getting an AC supply, we are supplying AC only to the load. Now, if we recall what is a rectifier, that is AC to DC. We get AC power from a supply, but what we get at the output is DC. But here this is dealing with AC only in the input and output sides both, but it is doing so in a control manner. That is, it is an AC to AC converter where we are allowing the AC input to be fed into the load in a control manner. That is, we are not allowing for the whole AC power in the whole input cycle to be fed, but we will be controlling it so that the load gets the supply, which is an AC supply, only for a certain period in the period of the input cycle. So, this circuit is having a resistive load RL. We are first of all considering a resistive load and we are applying a sinusoidal signal Vs, having two thyristors T1 and T2 as shown in figure. They are connected. So, now as this is an AC source, it is an input voltage which is a sinusoidal, and what will be happening in the positive half cycle of the signal? In the positive half cycle of the signal, this T1 will be having anode positive with respect to the cathode, and a lower thyristor T2 will be having anode, and the cathode will be positive with respect to the anode. If we consider this half cycle, positive half cycle, this one, then in this positive half cycle, this is T1 has anode positive with respect to the cathode, but this is here the cathode is positive. So, obviously the thyristor T2 will be not able to conduct, it will be turned off. The conduction can take place only in the thyristor T1, but let us assume that a firing angle or a delay angle of alpha is maintained. So, the thyristor T1 will fire with a delay angle of say alpha, and also one point to be noted here which is to be remembered are that the thyristor T1 and T2 are identical. So, we must be using identical thyristors so that the output waveform or output voltage which you get across this load resistance should be having symmetrical shape. So, T1 and T2 must be identical, and what will happen in the positive half cycle? Say at an angle of alpha, the thyristor T1 will be turned on, and when it turns on, the voltage across it will be 0. Now, what will be the voltage across this RL? Till the firing occurs, till the firing of this T1 happens, the voltage will be 0, because there will be no current flow in the resistance RL. So, till the firing takes place, the voltage across this resistance, which is say VL, this voltage let us name it as VL, the voltage across the load. So, that load voltage is 0 till alpha in the positive half cycle, because till this point the thyristor T1 is not firing, and there is no question of firing in the thyristor T2 also, as this is reverse biased. I mean, anode is cathode is positive where anode should be positive, and after this conduction of this thyristor T1, the thyristor will conduct. So, when the thyristor conducts, there will be current flow in the resistance RL. So, the voltage across this resistance RL, which is VL, will be nothing but the supply voltage, since the conducting voltage or the voltage of the thyristor after conduction or when conduction is going on is 0. That is, we have been assuming, because that on voltage, when the thyristor is on, that voltage across the thyristor is very, very small. So, it is almost equal to 0. So, the voltage VL is equal to nothing but Vs, as this drop is 0. So, we will be getting the output voltage across this load, which is VL, to follow the voltage Vs. This voltage Vs, whatever is given, it will be the same voltage. Now, this will continue till the input voltage, which is a sinusoidal voltage, crosses into the negative half cycle. It crosses 0 and becomes negative. And the lower one thyristor, now it will be properly biased, because now in a negative half cycle, what will happen is that the cathode of this T2 will be negative and anode will be positive. So, upper one, that is thyristor T1, will be now off, it will be turned off because of this biasing being reversed, but the thyristor T2 will be now properly biased, and using a proper gate pulse and a proper choice of the triggering voltage, we can now fire the thyristor T2 identically at an angle of alpha as in the upper one thyristor. So, in the negative half cycle, at an angle of alpha, it will be starting to conduct, and then current will flow in the resistance RL, and the voltage across this resistance RL, which is VL, will be same as the supply voltage, because this drop in the T2 is 0. That means, in the negative half cycle, if we look into till alpha, that means till firing of the second thyristor, the lower one thyristor, the voltage was 0 till this point, and then the voltage will follow the input voltage. That means, the voltage will be the negative half cycle voltage. So, this will be the load voltage or the voltage across the load. Now, if we consider the current through the load, as this is a purely resistive load, so the current will be simply VL by RL. So, the waveform of the current will be similar to the waveform of the voltage, only the magnitude will be differing, but the shape will be exactly same. So, we get the current through the load similar to the voltage, only that magnitude will be a little less because of the division by RL. So, depending upon RL, it will be having that magnitude. So, this figure is showing the load voltage and current in a resistive load. So, now if we want to find out what will be the values of the voltage, current, etc., we have to now mathematically proceed, and we have to use the expression for the input voltage, which is a sinusoidal voltage, which is expressed by Vm sin theta. Theta is equal to omega t. So, the sinusoidal AC input, which is Vs, is equal to Vm sin theta, where Vm is the peak value or maximum value of the voltage, and omega t equal to theta. Again, the maximum value or peak value of the voltage is equal to root 2 into V RMS. The root mean square value, if we consider, which is say Vs, Vs signifying the root mean square value of the AC voltage, which is the average quantity which is used to express an AC quantity, and root 2 times that RMS value will give you the peak value. So, in another way we can express it as root 2 into Vs into sin theta. Now, if we want to find out the mean current of the thyristor, now you can see that the thyristor is firing alternately. In the whole input waveform cycle, for half of the period thyristor T1 is firing is conducting, and for the other half thyristor T2 conducts, not for the exact half but less than one half, that is at it is firing at an angle of alpha. So, basically the thyristor is on from alpha to pi. Thyristor T1 is the thyristor T1, if we consider, it is firing at an angle of alpha and it is continuing to fire or continuing to be conducting till pi. So, if we want to find out the mean current for each thyristor, the thyristor current if we want to find out, then we have to find out by integrating Vm sin theta d theta by RL, because this is the current expression. Vm sin theta is the voltage which is being applied, divided by RL the load resistance, integrating from alpha to pi and dividing by 2 pi, because in the whole period of 2 pi is the whole period of the waveform which is given as input, but one thyristor is conducting from the thyristor T1, if we consider, it is conducting from alpha to pi, and the other thyristor which is conducting is from pi plus alpha to 2 pi. So, you can find out anyway, either you can find out the current in thyristor T1 or you can find out the current in thyristor T2, but you will have to integrate properly, that is within the proper limits. For the thyristor T1 we will have to take the limits between alpha to pi, and for the thyristor T2 we will have to take the limit between pi plus alpha to 2 pi. Now, doing this integration, what we will be getting is Vm by 2 pi RL, this is the constant part taken outside the integral, and integration of sin theta d theta, it is equal to minus cos theta, and putting the limits of alpha to pi, so we get this expression. Now, evaluating cos theta between alpha to pi, what we will be getting, minus cos theta, minus can be taken out. So, cos theta between alpha to pi, cos pi is minus 1 minus cos alpha. So, minus can be taken out, what we will be getting finally is 1 plus cos alpha. So, this is the expression for the average current in a thyristor, which is Vm by 2 pi RL into 1 plus cos alpha. Now, this is the average current, and if we want to find out the root mean square current, Trms square, let us first find out the square and then we can find out the square root to get ITRMS. Our aim is to find out ITRMS. So, you know that the root mean square value can be found out by under root 1 by 2 pi into integration alpha to pi by square of this I whatever we have found out here. So, this integration we can find out the RMS, basically the IT RMS, if we find out, that will be under root 1 by the whole period is 1 by 2 pi integration within the same limit alpha to pi. This square, the square is of IT mean square, which is actually this is, we have to find out the square of this term, which is this one, and integrate between alpha to pi, this is I square d theta. So, let us first find out the square of this term, that means free of this root, and then we will find the root to proceed in an easy manner. We are doing that. So, basically we are removing the root first. So, that means only the square value we are taking 1 by 2 pi integration from alpha to pi I square or the I average square, whatever we have got, is Vm square by RL square sin square theta d theta. Doing this integration will lead to, first of all, taking the constant parts outside, it will be Vm square by 2 pi RL square. Now, integration alpha to pi sin square theta d theta. So, integration sin square theta d theta between alpha to pi, that we have to do. So, for that we will be using the technique of cos twice theta equal to 1 minus twice sin square theta. From that we can find out what is sin square theta. Sin square theta is equal to uh, 1 plus cos twice theta by 2. So, if we use this sin square theta and represent this by 1 plus cos twice theta by 2, then we can now easily find out the integration. So, what will be this value? You take the integration of d theta, which will be giving you theta. So, theta, then of course half will be there, and plus integration cos twice theta d theta. So, integration cos twice theta d theta will be sin theta sin twice theta by 2, and within the limit alpha to pi. So, if we now replace the values of the integration, limit pi divided by 2 plus sin 2 pi by 2, sin 2 pi is equal to 0. So, that will be removed, minus alpha by 2 minus sin of 2 alpha by 2. So, if we consider this, we will be getting pi plus sin 2 pi by 2 minus alpha minus sin 2 alpha by 2. So, what we will be getting? I think there is a mistake in plus and minus sign, because we are sin square theta d theta. If we do this sin square theta d theta, what will we be getting? Sin square theta integration, and we know what is sin twice theta is equal to twice sin theta cos theta, and cos twice theta is equal to 1 minus twice sin square theta. So, twice sin square theta equal to 1 minus cos twice theta. So, it will be minus, I think. So, if it is minus, then it will be integration cos twice theta, then it will be the differentiation of sin theta is equal to cos twice theta. So, cos twice theta is equal to d d theta of sin twice theta is equal to cos twice theta. So, here integration of cos twice theta will be simply sin theta, sin. So, this minus sin will be, I think this will be, no, this is plus, here this is because of this integration sign of minus is there. So, finally, we will be getting this result. So, you have to just check this result, just see this plus and minus sign. So, finally, what will be getting, this is correct, pi minus alpha plus sin twice alpha by 2 by pi from limit alpha to pi. When I place, I will be getting this result, but this is I square. So, if I want to find out the root mean square, it will be square rooting of this figure, it will be Vm by 2 RL, pi can be taken out inside, and we will be taking the root of this pi as well as root of this whole thing. So, this 2 actually what is done, this 2 is taken out, it becomes 4. So, each root will be 2. So, it will be getting rid of this 2, and here it will be kept only 2. So, finally, this is the root mean square. Now, if we want to find out the RMS output voltage, similarly we can proceed, and we have the voltage Vm sin theta is the input voltage, and the output voltage which we will be getting, it is following the input voltage only. So, that sinusoidal voltage only, but its value we will have to take into note that its value when we take the limit is alpha to pi, but we are finding out the RMS value. So, the integration alpha to pi Vm square sin square theta d theta, but it will be 1 by pi, not 1 by 2 pi, because here we can see that we are finding out the RMS value of the output voltage, and RMS value of the output voltage, when I find out, output voltage is there or available for whole period from 0 to 2 pi. Of course, there are in between non-conducting periods from 0 to alpha, but we are finding out the RMS value or root mean square value. So, for the whole period we will have to divide it by 1 by pi here, because we are integrating between alpha to pi for one half cycle, but the consideration of the whole period is to be done, because the root mean square value, when we find out, we are finding out the root mean square value of the output voltage VL for this whole cycle between 0 and 2 pi, and out of this whole cycle from 0 to 2 pi, we are finding out from alpha to pi, because from 0 to alpha there is no conduction, the voltage will be 0, only the voltage will be here and again here. So, when finding out the root mean square value, we will be using that consideration that we are finding out from alpha to pi, and the integration of Vm square sin square theta, because here it is same shape of Vm sin theta, this is the voltage. So, we will be getting Vm square sin square theta d theta and multiplied by 1 by pi. So, this is the V naught square RMS, and in order to find out the root mean square, we have to take the square root. So, square root of this whole thing. So, by replacing these values Vm square by pi, pi by 2 minus alpha by 2 plus sin 2 alpha by 4. So, it will be giving you Vm by root 2, because 2 can be taken out, and inside this root pi minus alpha plus sin 2 alpha by 2, this pi can be taken in. So, this will be the result of this RMS value of the output voltage. So, if we now replace that Vm by root 2 is the root mean square value of the voltage, which is nothing but Vs, we can represent Vm by root 2 by Vs, and the rest of the quantity is same. So, this is the representation of the RMS value of the output voltage, and the RMS value of the output current can be found out simply by dividing the RMS value of the output voltage by RL. So, that is what is done, Vs by RL into this other part. And if we are if we are interested in finding out the RMS value of the output power, if we want to find out, I square R is the output power. So, I RMS square into RL, this is the output power. Replacing this I RMS by this value, which we have just now seen, multiply it by RL. So, if we square this value, this half will go, Vs square will be there, RL square into RL will be simply RL in the denominator. So, this term gives the value of the output power in RMS. So, here using a resistive load, we have seen that the output across the resistive load is following the input voltage, and there is conduction taking place for a control period, and by that we are basically controlling the power fed to the load. We are not giving the input power to the load for the whole time or the whole period, but we are only supplying the input power to the load for a certain portion of the time, and that is basically used for those applications where we are interested only of using the power for a certain period of time, not the whole period. So, that is going to reduce the power wastage also, where we do not want that the power should be consumed throughout the whole period, but we want that it should be only having the power only for a certain period. In that case, we will be using this converter, AC to AC converter. And one thing is important here is that till now we are only considering resistive or pure resistive load. So, if we have pure resistive load, things are easy or simple, because the current which flows through the load, it immediately stops to 0 as soon as the thyristor does not conduct. As soon as the thyristor is turned off, the current through the resistive load is 0. But we will find in the next classes that this is not true if we have a load which is not purely resistive, which has an inductive part. Suppose if we are dealing with a complex load having resistance and inductance both, then we will find that this condition is not going to happen, that is the current through the load will be not immediately becoming 0 as soon as the thyristor is turned off, because of the conduction, because of this inductor being present, inductance is there. As we know, there will be a flow of current even beyond the non-conducting moment. So, even if the thyristor stops to conduct, then also there will be current flow for a certain time depending on the time constant of the circuit, and because of which we will be having certain problems in the output voltage, because output voltage also will be accordingly, as we know that the output voltage across the load will be the product of the current and the impedance. So, if current is there, the output voltage will also be present even when the thyristor is not conducting, and we will be trying to get rid of these methods by using some techniques. So, that we will be discussing in the next class.